oxide. We're going to take an amine, we'll take methylamine, why not? Right. And I'm going to put these two reagents together. One's an acid, one's a base. And you have to figure out which is which. I want you to give a detailed reaction mechanism that predicts the corresponding conjugate acids and conjugate bases, and make an educated guess about which direction the equilibrium lies when this reaction reaches equilibrium. So in the next 60 seconds, I want you to give a detailed reaction mechanism that predicts the outcome of this acid-base reaction. It means you'll have to draw conjugate acids and conjugate bases and arrows. And I want you to make an educated guess about which direction the reaction lies at equilibrium. Again, 60 seconds, off to the races with you. Try your best on this. You should be able to do this based on what we did yesterday. If you can't, there's a major problem. Okay, so give it a try. Maybe surprise yourself. But again, next 30, 45 seconds, I'll be largely quiet here, but you have to be drawing. Right? That's all we did yesterday. So good luck. And again, you have to be able to identify one is acid, one is base. Once you do that, you have to start pushing arrows right away. And while this arrow pushing exercise is new to you, we did it for about an hour and a half, hour and 45 minutes yesterday. And again, if you put any time into practice rewriting these mechanisms, you should be able to do it with some level of confidence. Even though these are new molecules, don't panic. Maybe you make some mistake, but if you're stuck staring at this still, can't push any arrows, can't say, oh, this is the base, this is the acid, then you haven't internalized yesterday's lecture. Today's lecture is going to be that much more challenging for you. You're going to be further behind. So I really hope you took serious what I said yesterday and put it into practice. These two particular molecules, hopefully you identify this one as base and this one as acid. If that's not what you did, well, then you can at least try things and you'll run into problems eventually. Base has some clues. This is sodium methoxide. It's a close cousin to sodium hydroxide. So, you know hydroxide's a base. We used compounds like this yesterday in class. This particular molecule, if you define it as the acid, there's two types of different protons on it. There's NH or CH. Periodic table trend tells us that the NH protons are significantly more acidic than the CH protons. So there's no reason why we should try to pull off this proton when we have these two that are thousands or billions of times actually more acidic. The arrow pushing exercise starts from the base and goes to the acidic proton. This will be the formation of the new bond. Hydrogen doesn't want two bonds. The bond between it and nitrogen breaks. Then we have some equilibrium. We'll leave this blank right here for now, but we have to draw the resulting conjugate acids and conjugate bases. If you don't know how to do this arrow pushing activity, you still should right away be able to at least draw methanol. That's the conjugate acid of methoxide. And then you should be able to draw some version of amide or nitrogen with a negative charge on it. And there's a sodium floating around. I don't care about that so much. All right, but you should be able to do this quite rapidly. Okay? We know then that this is the conjugate acid. And if we do a direct comparison between this and this, we can figure out which direction this lies at equilibrium. Well, alcohols, we said the pK was about 16. And amines, somewhere in the 30s. I don't have the number off the top of my head. You should have memorized it by now. Let's say 36 or 38, something like that. Okay, so this particular reaction, when it starts, this is a base, pulls off this proton, makes this conjugate base and this conjugate acid, but at equilibrium, it's making things that are more reactive than what it started with. And so at equilibrium, the arrow should look something like that, facing the starting acid and base pair rather than the resulting acid and base pair. One other thing we can say about these compounds, conjugate base. So this is the stronger acid for sure, 100%. Hope you figure that out just by the pK numbers I asked you to memorize. And again, we didn't look at methylamine, but in general, this is an amine, and the ammonia group that I gave, the pK is about 36. So you should have some feeling that there's this difference. This is 1 times 10 to the 20 zeros more acidic than this one. Okay, so we know that this is the stronger acid, so then this must be the weaker base. This is the weaker acid, this must be the stronger base. Notice how the stronger reagents are on the same side as usual, and they're obviously going to favor the weaker reagents. So this is just a quick reality check, turned into a 5-minute discussion for us, but if you did fine on this, great. If not, then you have a lot of things to work about. In particular, these arrow pushing activities, the newest thing for us, it's intellectually the most challenging thing for us. It's the thing where you can't make mistakes on. You have to master this quite quickly, because we're going to do it every class from this day forward. We're going to now just revisit and roughly go through the pre-lecture video that I went through yesterday with us. We're going to talk about and revisit 4 factors that influence acidity, right? And we have to have some working understanding of these factors to be able to look at molecules and predict whether they're acidic, whether they're basic, and how they might react. The first factor we spent a lot of time yesterday was the periodic table trend, right? This particular trend tells us in the periodic table that acidity, if we're comparing CH and then over here HF and down here HI, it increases going from left to right and from top to bottom in the period. Okay, so in a column, increases going down and from left to right. The corresponding, if we're looking at conjugate bases, we know that conjugate bases are, so this is acidity, and conjugate bases would follow the opposite trends. If we had I minus, F minus, C minus, these types of things. So this is just a simple periodic trend. We don't need to discuss it any further. We've talked about it quite a lot. But we're going to talk about 3 things today. We already know what the prelude is for them. We're going to talk about induction. This is related to bond polarity and electronegativity. We're going to talk about resonance, an increasing important phenomenon in this class as we move forward. And we'll talk about hybridization. And again, this is going to look a lot like the pre-lecture video that I gave you yesterday, where we're going to be writing this out. You should be rewriting these things as you study, making notes and trying to put to memory or deep-seated understanding these kind of concepts and ideas. We're going to talk about resonance and induction kind of hand in hand together. And you don't have to be experts in these high-level kind of ideas, but you have to have a working understanding of them so that you can apply it to new problems that we see. I think the best way for us to talk about induction and resonance today will be about with 2 functional groups, organic function groups that are really common, that can be viewed as acids. Regular alcohol, we said yesterday, has a pKa roughly 16, and carboxylic acids, our kind of frame of reference is 4.75 for acetic acid when this is a methyl group. And if this is a methyl group, we get pKa of about 16. So these are acidic, but methanol is not terribly acidic, and acetic acid is somewhat acidic. Carboxylic acids, as the name implies, are acidic, right? So this is kind of a tautology here, dumb thing to say. Let's just say that carboxylic acids are acidic. And they have a Ka, or an acidity constant, roughly 10 to the minus 4 to 10 to the minus 5. And this translates into a pKa between 4 and 5. Okay, we'll talk again a little bit about Ka, a little bit about pKa, but you're not going to be calculating these things. But you have to have a rough feeling about how this works. In our first pre-lecture video, I put up the balanced reaction equation for acid-base reactions in water. And we're going to actually use this as a tool in our class today. We're going to keep drawing this equilibrium reaction. We're going to write out when we have an acid in equilibrium reaction with it and water to understand better this stabilization effect of conjugate bases that was a new topic we introduced in our last class, or our last pre-lecture video. We're going to take carboxylic acid and water. They both have a pKa that's appreciable, and that we know, 4.75 and 15.7. When these go into water, this is much more acidic than this, so water can act as a base. And from a mechanistic point of view, we'll draw these 2 red arrows. The base attacks the acidic proton on the carboxylic acid. It's going to start forming a new bond with oxygen. And Hydrogen doesn't want two bonds. This weak bond here that goes to oxygen breaks, and we end up drawing the resulting conjugate base of acetic acid, and we draw the conjugate acid of water, which is known as hydronium ions.